Okay, I'm going to repeat this problem. This was done with special points earlier. This time I'm going to use the vector loop method. In order to do a vector loop method, you do the same thing as before. You identify special points, the number of rotating bodies, all of those things. And then you write a loop. You begin at any point. It's completely arbitrary. And you walk around the mechanism. And so what I'm going to do is I'm going to begin here. Put it in a different color. I'm going to begin at point D. I'm going to walk to C. Then I'm going to walk to D. And then I'm going to walk back to D. So I'm going to go from D to C to B back to D. Okay. And like usual, I'm going to put I to the right. I'm going to put J up. And K is going to be counterclockwise, as usual. Okay. So now, if you're going to walk from D to C, you're going to go a distance right to here, and that is a distance of 0.3 times the cosine of theta. And when you're doing these, you want to make sure that you use everything that's a variable. You want to treat it as a variable. So even if the problem were to say theta is equal to 60 degrees, you don't put in 60 for theta. You leave it as theta because it's a variable. It can change, right? So anyway, I'm going to walk that distance, and I'm going to go backwards. I'm going to go left. So it's a negative I. And then I'm going to go down this distance right here. And that distance is 0.3 times the sine of theta. And I went down, so that's a negative J. So now I'm standing at point C. So if I'm going to go from C to B, I'm going to go a distance, horizontal distance. I'm going to go, let's put that in a different color. I'm going to go this distance right here, this distance here. All right, and that is 0.3 times the cosine of theta. And that I'm going to go that distance left. Then I'm going to go up a distance of 0.3 sine of theta, and I'm going to go up, so that's a positive J. So now I'm standing at point B right here. And now I'm going to go back to D. So I'm going to go a distance of x, and x is a variable, and I'm going to go to the right, so that's going to be a plus. When I get back to where I started from, I'm back at the origin, so I'm back at 0. I haven't gone anywhere. Okay, so this is my vector loop equation, and if you want to, you can solve this thing for angles. So what you would do is, in order to solve that guy, you're going to pull off all the i's. On the left, you set it equal to the i's on the right, and j's on the left equal j's on the right. So what that is put off the i's, that's a negative 0.3 cosine of theta minus 0.3 cosine of theta plus x, that equals 0. And then the j's on the left, that'd be a negative 0.3 sine of theta plus 0.3 sine theta, that equals 0. Okay, and then there's obviously no k's on the left. That would be 0 to 0 if you had any. So anyway, you have two equations, and you have two unknowns, theta and x. So what happens here is this guy comes out to be 0 on the left equals 0 on the right. It's true, but it doesn't help you any. The top equation tells you how to solve for x. X is equal to negative 0.6 cosine of theta. Okay, and you could look at the geometry and do it as well. But the power of the vector loop is the fact that if you can't see the geometry, it will give you the equations that solve for the position. Okay, the next thing you do after you write your position equation, probably even before you solve it, is you're going to take a derivative. Now, it's possible that if you had gone ahead and done this step where you pulled off the I and the, I equal I, J equal J, if you want to, you could take a derivative of those. I tend to be, I like to use Mathematica, so I don't want to pull things off like that. So I just take a derivative of the original equation. So in other words, I take the derivative of this one here. Okay? So that's what I'm going to do. I'm going to take a derivative of that. Keep in mind that theta and x are variables. Okay? And don't forget the chain rule, right? Okay, so if you take a derivative of this, I'm going to end up with minus 0.3. Derivative of the cosine is the sine of theta times theta dot I. And then, because I, j's, and k's are constants, right? Minus 0.3. Derivative of the sine is the cosine of theta times theta dot, chain rule. J is a constant. And then I have the blue row, that's going to be 0.3. Derivative of the cosine is negative sine. Oops, I made a mistake here. Derivative of the cosine is minus sine. Okay, 0.3 sine of theta, chain rule, theta dot, I. Keep going, plus 0.3. Derivative of the sine is the cosine of theta, chain rule, theta dot, J, and then plus x, that would be x dot, chain rule, x dot I, and that equals 0. Derivative of 0, 0. Okay, so now for this equation, you can pull values off and solve for the velocity terms. So i's equal i's, j's equal j's. So that would be 0.3 sine theta, theta dot, plus 0.3 sine theta, theta dot, plus x dot equals 0. And then the j's, minus 0.3 cosine theta, theta dot, plus 0.3 cosine theta, theta dot. That's it, so that equals 0. This equation doesn't help you much. It's, on the left-hand side, you get 0 equals 0. It's true, but doesn't really help you any. They don't always cancel like that. This one happens to be just symmetric, and so that's why it's doing that. Okay, the top equation then looks like this. It's x dot is equal to 0.6, negative 0.6 sine of theta times theta dot. Okay, so now the question is, how is x dot related, or anything related to what you know? And by the way, it's 1 degree of freedom. That means if you know one of these, x dot, you can find theta dot. If you know theta dot, you can find x dot. But you got to know one of them, which you do. Okay, so look at the picture now. You know that this velocity here, v, is on a body that is not rotating. So his velocity right here is equal to v, and it's going in this direction here. Okay, so here's the thing. How is v related to x? Well, first of all, make sure that x is being measured from a fixed point, because if you're trying to relate the derivative of x dot, and you want to relate that to velocity, you've got to measure x from a fixed point. But fortunately, I am. I'm measuring it from v, which is fixed. So x dot is a velocity. Okay, now, if v is moving to the left with a speed of v, like 3 feet per second, then the x is getting bigger, right? If v is moving left, x is getting bigger. If x is getting bigger, x dot is a positive number, and if v is moving 1 foot per second, then x dot is increasing by 1 foot per second. So x dot is equal to v. So that would be x dot is v. So if you solve for the theta dot is equal to v negative v divided by 0.6 sine of theta, which is exactly what I had for the special point solution. Okay, now let's keep going on and finding the acceleration terms. So again, you could take the derivative. If you want to, you can take the derivative of these equations, or what I like to do, because I like to use Mathematica, I'm going to take the derivative of the blue guy. Okay? So here's what I get when I take the derivative of the blue guy. And again, remember, chain rule. So I'm going to treat this guy as a product. Okay? So it goes 0.3, derivative of the sine is the cosine, chain rule, times the derivative of the second term. Plus the first term times the derivative of the second term. And then I have the second term, 0.3, derivative of cosine is minus sine, that's why I changed that. Right. Sine of theta, chain rule, times the second term of that guy, minus 0.3 cosine theta, theta double dot, j, plus 0.3 cosine theta, chain rule, theta dot I, plus 0.3 sine theta, theta double dot I. Keep going, minus 0.3 sine theta, chain rule, plus 0.3 cosine theta double dot j, plus x double dot I equals 0. Okay, so the hard part really is taking the second derivative. That's why Mathematica works really well. That way you don't make mistakes. But anyway, I'll show you that in a little bit. Okay, so here is, again, what you do is you pull off the I equal I, J equal J. So what you have is 0.3 cosine theta, theta dot squared, plus 0.3 sine theta, theta double dot. Let's see, plus 0.3 cosine theta, theta dot squared, plus 0.3 sine theta, theta double dot. Let's see, that guy here is a, I forgot this component, so this term here is a j. Alright, plus x double dot equals 0. Then you pull out the j's, so I have a 0.3 sine theta, theta dot squared. I have a minus 0.3 cosine theta, theta double dot. I have a minus 0.3 sine theta, theta dot squared. And I have a plus 0.3 cosine theta, theta double dot, equals 0. Okay, the bottom equation, just like before, doesn't help you because all of these terms cancel out and you're left with 0 equals 0. It's true, but it doesn't help you. Okay, now, solving the top equation, you get, I'm solving for theta double dot, so that would be, let's see, got this term and this term, they're identical, so I've got two of those, so it's 0.6 cosine of theta, theta dot squared. So I've got that term, I get plus the x, plus x double dot, equals, and I'm going to throw the double dot terms over to the side, so I'm going to end up with a negative. I've got one of them, and I've got another one identical, so that's going to be a 0.6 sine theta, times theta double dot. Okay, so, oops, okay, so just divide through by this term. I have a negative 0.6 sine of theta equals theta double dot. Okay, now, x double dot is related to the acceleration of this term. Again, just like x dot is equal to v, in this case, x dot equals plus or minus the a. Now, if a is going right, like it says, the x double dot should be getting smaller. So if b is accelerating to the right, then x double dot is getting smaller. So it's going to be a negative. So x double dot is equal to a negative a. So what we'll do is we'll put in right here, this term is a minus a. And so theta double dot is equal to this. And that's the same solution that I got with special points. So what you can see is that when you can use the vector loop equations, they tend to be a little bit easier and quicker to use, but you have to be able to see the vector loop. Also, the big problem here is taking the second derivative. Okay, so that's it for this one.